Swayam Prabha. Digital India. Educated India.
Now, another behavior which is related to creep or which is happening parallel to creep is a relaxation behavior. Now, before we talk about relaxation, which is on the right side, I will talk about the creep, which is on the left side on the slide first. So, let us focus on the left side. What you see is the first graph is a time versus stress. Okay. Now, what it means? The stress is constant over a period of time. The stress is constant over a period of time. This is an example. You can see cloth hung on a string. Now, here the load of all these shirts, you can assume that to be the, because of that there is some stress acting on the string. Now, at one point it is unloaded, you take the cloth off, but that is fine. So, let us say this load is applied and here you have an elastic strain. The moment the shirts are put on the string, you have some strain which is immediate strain. The string which was horizontal, immediately it will sag, right? That is indicating of the elastic strain. Now, the cloth is already there. If you leave the cloth for some time period, okay, then the string will still experience some deformation, like this is the creep deformation. And I am talking, I know that you do not put the cloth for more than a day, but this is just an example to show you, which you can probably relate easier. Assume that this cloth is there continuously on the string for every day for months, okay. Then you will see that the deformation or the length of the string keep on increasing, or the sagging is more and more, okay. I am talking about this height is what I am talking about, this gap, okay, that is going to be more and more. Then when the load is removed, it will come down. So, you will recover some part of the strain that we call elastic rebound, mainly this portion which elastic strain, most of that is recovered. Then you will also have some more recovery, which is elastic plus the plastic recovery, okay. So, that is this portion here, and some point over here there are some region which is, some of the strain which is not recovered at all, that is permanent deformation. This you cannot recover, that is a permanent deformation you are talking. Now, that is about creep. Now, let us talk about the relaxation. Here strain is constant as a function of time and not the stress, okay. Strain is constant as a function of time. Now, when strain is constant, what is happening? Stress is coming down, okay. So, some realignment happens within the material, and because of that the stress experienced by the material comes down. In other words, the material cannot take any more load as expected, and this has become a big problem when you talk about pre-stressed concrete. Example, you can see here one picture I have put on the right side, where we use this pre-stressing steel strands, and then you have this is used on large concrete girders, etc. Now, pre-stressing strand, when you pull it, okay, you pull the strand and then anchor it and leave it so that the concrete will be under compression, that is the idea. Now, when you pull the strand, the strain or the distance from the end to end of the strand is constant, or the not that distance, sorry, the extension which you provide, right. So, let us say you are pulling the strand and the strain at that moment in the beginning is almost same after some time also. In other words, there is no reduction in the strain because the length of the girder remains same, okay. Now, strain is constant, but if there is a realignment or some changes happening within the material of the strand or steel, then it will lose the stress. And if it loses, then we can call it the strand has relaxed and it will not be able to provide the same stress as it was giving in the beginning. And when that happens, the pre-stress concrete's capacity will reduce. So, the pre-stress loss should not happen. Okay. So, more on this you will understand when you get to courses on structural design, etc. But the material behavior, very important for pre-stressing strand is that it should be of low relaxation. The strand should be of low relaxation. You should look for this. Okay. It is very important when we talk about pre-stress concrete. Now, we talked about elastic behavior, we talked about viscous behavior. Now, let us see how we can model this. Elastic behavior you have seen many times, we can model by using Hooke's law. Okay, spring constant, you have seen that also. Here you can see as a function of time, a load F is applied, as a function of time the deformation. The moment the load is reaching this point, the deformation is also at that point. I mean it experiences the same. Okay. But when the load is released at this point, deformation also becomes 0. It comes down to 0. So, this is a pure elastic behavior. When you talk about viscous behavior, you see the load is applied and then load F here. At that moment, the deformation is 0, but it is slowly increasing, and when the load is removed, at that point there is a deformation and that deformation stays constant. It does not come down as in the case of spring. So, these are two different basic elements which can be used for modeling viscoelastic behavior. Elastic behavior on the left side, viscous behavior on the right side. Now, how do we combine these to model a viscoelastic behavior? Okay, let us see that. So, here is an example, I got it from one of the YouTube video, you can watch that video, very interesting. Link is given at the bottom left. These are some snapshot from the video. So, you can see on the first image, that is a spring model. Okay. You can see the spring. So, I am filling the yellow region is the graph corresponding to the spring model. Okay. So, time t0 is this. Okay. Now, after that, so before I go into the graph, let me show you what this model looks like. So, this is a spring model here, and then you have a spring and dashport placed in parallel, which we call Kelvin model, and then you have a third one which is a dashport model alone. Okay. So, these are spring, Kelvin and dashport put in series. Now, the first one on the top left is the deformation due to spring model or immediate deformation. Second one is Kelvin model, which has spring and dashport. The blue region is because of the viscous flow. Okay. So, you can see at the background of this curve, you have a spring shown and also a dashport shown. Okay. Now, spring plus dashport, sorry. Now, the third one is of the viscous deformation, which is only the dashport, this green one. Second one, let me correct that. Second one is spring plus dashport in the blue. Over here, it is spring plus dashport, and here it is only D and spring plus dashport, and this is spring. So, I am just keep on adding to the top. First, I talked about the yellow, which is only spring, and then I talked about S plus D also added to that. Then on top of that, D is also added. So, over here in the bottom left, S, and the second one is S plus D, and the third one is D. This is just a summation of all three. That is what you are seeing on this graph here, which is very similar to the graph in the previous slide, this one. So, the creep graph here the creep graph here, it is very similar. Okay, you can see the shape, trace the shape of this, it is coming something like this. Now, the same thing is here also, you can see this graph, it goes something like this and then comes down and then goes. Okay. Now, here you can see the load is removed at this point and then you have spring recovery and then you have spring plus dashboard recovery and then you have permanent deformation. This is permanent deformation, this is spring plus dashboard and this is spring. Okay. That is about the Berger's model of viscoelastic behavior. Now, these viscoelastic behavior is also dependent on the temperature and time, loading, etc. So, when there are small changes in temperature, that is also affecting the behavior in of these materials. Mainly it affects the plastics and asphalt materials, and the material gets softens at higher temperature. I mean, that is as I anticipated, like something when it is hot, it flows far easily. When it is colder, it will flow, and it will be difficult to make it flow, and softens at higher temperature and hardens at lower temperature. So, look at the graph on the right side bottom, you can see these soft, hard, and as the temperature increases. So, as the temperature increases, the material becomes from hard to soft case. And so, in reality, how do we look at this temperature increase? When from winter it will be temperature will be low, in summer temperature will be high. Okay. This is during service, this happens during service, every year it happens. Now, there is also a case where this material experiences much higher temperature, that is during construction. You will be actually melting, or sorry, you will be actually heating the asphalt or bitumen to to make it flow during the construction, right. So, that time during the high temperature of even at this temperature, the material will be very, very soft. Okay, it will be very soft, or it will flow easily, whereas in winter it will become very hard. Okay. Now, imagine a road which goes through a region where the climatic variation is significant, very cold in the winter and very hot in the summer. So, how do you set this this material so that for both winter and summer it is in the reasonable, the softness or the viscosity is in the reasonable limit. So, you will have to look at the temperature range which is in service, and during that temperature range whether the material is having sufficient viscosity or not. Okay, it should not be very, very fluidy, it should not be very low, it should be viscous enough so that it doesn't flow easily. Okay. So, these parameters are important when we talk about adhesion, rheology, durability and many other things during temperature which are so the temperature at the construction site or the ambient temperature conditions for the material throughout the year must be considered before you select a material. Okay. So, the picture on the top over here is basically how these typical asphalt materials are tested. Okay. So, this PEN here is the penetration. Okay. This is a test which we do in asphalt. You will do this test again in some other class, but penetration, you basically take a needle and put it through the asphalt and you see how much is the depth of that penetration. So, if the material is more fluidy or less viscous, it will penetrate more. So, we will put some limits on how much it should penetrate. This is how it is handled in the construction site. And VIS is viscosity, we will put a limit on viscosity also and penetrate. So, these are the approaches by which we control these properties of various material. Now, last point on this slide, metals or concretes are relatively less affected because of the temperature. I am not going to say it is not affected, it is affected, but relatively less. We will show some example on that also later. Now, viscoelastic materials are affected by the load rating and duration. You can see here fast vehicles, when the vehicles are moving very fast as shown in this picture, the deformation is less. When you have a parked vehicle, you will see more deformation like you see in the marking here. You can see imprint of vehicles. If you imagine you park during the summer and there is some bleeding also on the road, the tar bleeding or the bitumen bleeding, you will see imprint of your vehicle's wheel. And that is a it's like when you say the vehicle is parked, the duration of the load application is more, the time, the duration is more, and hence you see more deformation on asphalt, even though the weight of the vehicle might be less. In other words, you can even have an imprint even if it is a cycle, for example. Okay. But on the fast moving vehicles, even at a higher load, you will not see as much deformation. That's what you have to look at. So, you have to look at the time, duration, and also the value or the magnitude of the load. Both are important to consider when we think about deformations here. Now, another behavior which is mainly for metals is temperature effect is the ductile to brittle transition. In the previous slide I mentioned, previous slide, the last point was metals can also have some influence because of the change in temperature. So, this is on that. So, in many materials the failure mode changes from ductile behavior to the brittle, or the from ductile failure to brittle failure as the temperature decreases. Now, normally this transition occurs over a range of temperature. It is not sometimes it happens in 5-degree change or something. We are talking about larger range. I will show a slide a picture on the next slide. Now, in what type of metals this happen? It happens when you are talking about face center cubic lattice structure, typically aluminum, copper alloys. Okay, they remain in those it does not happen. In FCC alloys it does not happen. That means they remain ductile even at very low temperature. Okay. But when you talk about body centered cubic or hexagonal crystal structures, you have DT-BT transition, which is very common. Okay. Now, most ceramics and polymers also experience DT-BT. Okay. Now, this is a graph which shows how this you can see temperature here and then impact energy absorbed. So, when I say why we are looking at energy is when we talk something is behaving in a brittle manner, that means it takes less energy. Okay. If something is ductile, then it takes more energy. That is the concept. So, I am going to show you a small graph here, which I will delete later. So, if this is strain and this is stress, a material which has a graph something like this and there is a breaking point, we can call it as a brittle material. Whereas, another graph, if it goes something like this and then it breaks here, then we can call it ductile behavior. Okay, ductile, and this is brittle. The longer the area under this curve, the larger the area under this curve, and if the width is more, then we can generally conclude that as a ductile material. Whereas, if the width is less, like in case of B, brittle material here, the width is very little, this much only. So, that is a brittle behavior, whereas in case of ductile material, it is much wider, the graph is much wider. So, it is a ductile behavior. So, looking at the energy under the area under this curve, that is what we really look at. Okay, that is the energy. In this case, this whole thing is the area. So, for the ductile material, you have more energy. So, I am going to delete this. So, we can. Okay. Now, here, so that is what we are talking, energy required to break. If it is more energy required, then I can call it as a ductile material. If energy required is less, then I can call it as a brittle material. Okay. Now, looking here, let us say you are talking about the mild steel, BCC or the red curve here, the mild steel which is showing the red curve. So, I can say that dTBT is somewhere in this region, right. So, I can say, or in what I am looking at is where is the maximum slope of that curve, okay, where the slope of the S-shaped curve is greatest. So, in this region I can say that mild steel will undergo ductile to brittle transition. That means, when the temperature is about, let us say, we can even call this whole region, I mean from here onwards, let us say about minus 25 degrees, if that is from here, the slope is very high. That means, let me call it, from here if I take, the slope is very high from here onwards. So, the material start behaving like a brittle material from about minus 25 degrees. If this is minus 25 degrees, from there onwards, as you reduce the temperature, the mild steel behaves like a cast iron. Cast iron is very brittle. Okay. Now, but copper, which has face centered cubic structure, it does not change even for up to minus 150 degrees, it does not change. Okay. This is probably one reason why copper pipes are even used for water supply systems in very cold countries. Now, for zinc, hexagonal and for nylon also, you can see there is a significant change even at very high temperature, you can see that. So, that is why this plastic, some of these plastics, they do not behave in a very ductile manner even at 0 degrees Celsius. So, for example, zinc here, you can see it is changing somewhere here or maybe here. So, you have to look at the slope where it is changing significantly, and then beyond that point, beyond when I say more negative to that point, maybe it is not recommended to use that material if you are expecting a ductile behavior. Okay. Because for all safety purposes, we want our systems to be ductile in nature, and this is why we are moving away from using cast iron. So, old times, people used to use cast iron for building, for structural steel, and then they started introducing steel, and then they found, because in cast iron the carbon content is very high and that leads to brittle behavior. So, you do not want catastrophic failures, you want the structure to deform before it collapses. So, we want ductile structures. So, started using steel, that is how the change came, but this steel will become brittle when the temperature is less than minus 25 or less than that. Okay. Two examples of a large scale failure because of this ductile to brittle transition. One is about the Titanic ship. Okay, what happened, the story, these are the locations where the iron rivets were used. You can read the story in the paragraph on the top left. You can pause a bit and then read the story, but main concept here which I am trying to say is that iron rivets or poor quality rivets were used, and when they hit the iceberg, there are different theories on this, but one theory is that this material which was used was it behaved in a brittle manner and led to the complete failure of the rivets, which further led to the collapse or the sinking of the ship. As you can see, that is also associated with the hull design. You can see this different compartments, but water was not moving from this compartment to this compartment, it was not allowed in that design. So, later on this failure also changed the way the ship hulls are designed. If water was going like this to all the hulls, then it would not have failed like this. So, because of this heavy water on the right end, then the weight was like acted like this, and then the ship broke over here. This is what happened in Titanic ship. Anyway, point for this class is that the material which was used for rivets became more brittle when it went through the Atlantic Ocean and near the iceberg, temperature was very low. So, the material which was ductile in Belfast where it was made or during the construction time became brittle during the service, which is as you sail through the ocean, cold water. Okay, that's what led to the failure. This is the story. You can read the story more detailed. Okay. Now, another example of such failure is the failure of Liberty ships in World War II. Here also you can say this is failing, like, broken into two at the center, and this is also associated with the ductile to brittle transition of the material which is used, and it led to the breaking of the ship into two and then sinking, and people were thinking that actually it is lost or the just disappeared in the North Atlantic and were falsely chalked up as lost to German U-boat torpedo attacks due to low temperature brittle fractures. So, material science really, but it took several years for scientists to confirm this behavior, and so this was written not until 1947. Okay, so several years it took before real reason for the missing ships were identified. Okay, so to summarize, we looked at viscoelastic behavior, we looked at creep and relaxation, very important for pre-stressing strands, the relaxation behavior, and then we also looked very briefly on how to model these viscoelastic materials, and then looked at temperature effects and looked at the viscosity, how viscosity of materials changes as temperature increases, and how the ductile to brittle transition happen as temperature decreases. We also talked briefly about the load rate and its duration, how that affects the flow of materials which are used for construction. Example we used was asphalt. I think with that we will conclude today's lecture. Thank you.